Hello everyone. In continuation to our previous video, in Theorem 1.5, we have learned that a rational number of the form p by q, which is a terminating decimal expansion, its denominator q will be of the form 2 power n into 5 power m. And in converse to that, we also have learned that in Theorem 1.6, a rational number whose denominator is of the form 2 power n into 5 power m is always a terminating decimal, right? Okay. Now, the question comes, what if the denominator is not of the form 2 power n into 5 power m? According to the previous video, Theorem 1.5 and 1.6, the denominator which is not having 2 power n into 5 power m should not be a terminating decimal. Let us check this with the help of some examples of rational numbers whose denominator does not contain 2 or 5 as factors. Let's check some examples. Let us take an example of a rational number whose denominator is not either factor of 2 or 5. Let us take like 2 by 3, where the denominator is 3 here, which is not a factor of either 2 or 5. So let us take 2 by 3 and put it in the form of decimal by dividing 2 with 3. So let's start doing division. 3 zeros are 0. So 2 minus 0, 2. So let's continue the division by putting a decimal and continue. 20, 3 put a decimal point, 3 6 are 18, 2 remainder, again drop one more 0, 3 6 are again 18. So as you continue the division, always you'll get a 2 remainder and 6 is repeating always. So you have a particular type of repetition. So we call it as a non-terminating repeating decimal. It is a non-terminating repeating decimal. It does not terminate. Non-terminating decimal. Or you can also call it as repeating or recurring. Repeating or recurring decimal. So, now what did we understand? If the denominator is not of the form 2 or 5 as a factor, then it definitely not terminates. It is a non-terminating or repeating decimal. Okay, let's do with another example also. Let us take an example of 1 by 7. Let us divide 1 with 7. So let's start doing. 7 zeros are 0 and 1 is the remainder. Put a decimal and continue the division by adding a 0 to side and put a dot and continue. 7 ones are 7 and continue. 10 minus 7 is 3. So add one more 0 and continue the division. So 7 fours are 28. 2 is the remainder and continue the division. Add one more 0. 20. 7 2s are 14. Let's move the screen a little bit. Yes. 7 2s are 14. Take 6 is the remainder and drop one more 0. 60. 7 8s are 56. 4 remainder and drop one more 0. 7 5s are 35. Again continue. 5 is the remainder and drop one more 0. 7 7s are 49. So let's continue. 7 7s are 49. Right, next 1 is the remainder. So from here onwards, the same pattern from here, what we got, the same pattern starts from here. So we can stop the division and write like 1 by 7 is equal to 0.142857. After starts again 1428557 and so on. So this particular block will be repeating always. So we can write it as 0.142857 bar. Okay, bar to this part of the block where it is repeating. So now finally we came to understand that if the denominator is 7, which is not a factor of 2 or 5, is also a non-terminating again. So like this you can take many examples which are not factors of 2 or 5 in the denominator, and you can check the division. There will be definitely non-terminating decimals or you can call it as repeating decimals. Repeating means the certain part of the quotient will be repeating. So they are repeating. So finally we can conclude that the denominators which are not a part of, which is not a prime factorization of 2 power n or 5 power m, then it will be definitely a non-terminating decimals. This leads to theorem 1.7. This is the theorem 1.7. Let's go to the theorem 1.7 now. Let x is equal to p by q, where p and q are co-primes, be a rational number such that the prime factorization of q is not of the form 2 power n into 5 power m, where n and m are non-negative integers. Then x is a decimal expansion which is a non-terminating or repeating or recurring decimal. Right? We understood that if the denominator is not of the form 2 power n into 5 power m, then the decimal expansion is non-terminating repeating recurring decimal. So this is theorem 1.7. So now let us continue some more questions in exercise 1.4. Thank you.